Hi all.
So the idea, I mean, you had a lot of interviews I saw on the YouTube, and you had one interview last year after you got the Berkeley Prize, I think.
Yeah.
So here we're doing a little bit different thing. The main idea is, I assume the audience will be like a PhD student and postdocs. Instead of hearing just the science,
Yeah.
they want to hear the stories and your insight, right?
Okay.
So they want to get something. Eventually, they want to be as successful as you. So that's the type of question I'm going to ask.
Understood.
All right. I'd like to start from something you mentioned during your talk.
Mm-hmm.
So the instrument part.
Yeah.
Right. So you mentioned that the commercial instrument can only get to a G ohm. And you're able to, this takes, I assume, take a long time for you to achieve there to get the mega ohm.
Yeah.
So what motivated you to, go through, beyond the commercial
Right.
available there?
Okay, that's a very good question. So, my former postdoc, Mohammed Hamidian, is the one who solved that problem. So, if you try to design a Josephson STM, then you have for superconductivity. Then you have a superconducting surface and a superconducting tip. Now, there's a famous equation called the Ambigar-Baratov equation, which tells how big is the Josephson current as a function of the energy gap of the two superconductors and the junction resistance, okay? And the current obviously will grow as 1 over the junction resistance, right? So you can write down that equation. You can say, suppose I have niobium and niobium. At what junction resistance would the current be big enough so that the Josephson energy is less than kT? Is greater than kT. You need the Josephson energy to be greater than kT. Otherwise, there'll be fluctuations in the phase difference between the two superconductors. So you have two constraints. One is the junction resistance, and the other is the temperature.
Okay.
Right? So when we were designing our second STM at Cornell, we worked out all those equations. And what you find out is that if you want to work at a gigaohm, if you want to have a normal state junction resistance of a gigaohm, but you want to detect the Josephson current, then you'd have to cool to microkelvin. Okay. Even today, that's impossible. Now, if you want to have a normal state junction resistance of, say, 10 megaohms or below, then you only have to cool to 100 millikelvin or something like that. So the design criterion for that machine was dilution fridge STM, ultra low vibration. You have to have ultra low vibration because if you want to make the junction resistance 1 megaohm, then the tip is only a few tens of picometers from the surface. But if the vibration level is in the picometer range, then the experiment will fail. Right. So you have to do 3 things at the same time. Say 100 millikelvin temperature, ultra low vibration, Josephson electrodes. Okay. And that was the reason why we did all the design work to make sub-Kelvin Josephson STMs be in the ultra low vibration limit.
So I have to imagine there must be some very challenging technical aspects.
It's extremely challenging technically to make an ultra low vibration STM for operating at mega ohm junction resistances in an active refrigerator, which can reach 100 millikelvin, 50 millikelvin. That took years of effort to do.
I see. So when you started this, do you think, okay, we'll be successful? You feel like it could fail, or?
I apologize. I don't think that way. So.
Okay.
Yeah.
So you think it will be?
No, I believe that fundamental equations of physics, and so I follow them, and so far I have found out that they're correct.
I see.
Ambigar and Baratov are correct. Josephson is correct. That's it.
Yeah, but in theory it's correct, but technically, some people will say, "Oh, this is too challenging. I'll give up."
Okay.
Yeah.
So, yeah, that's true, and that's true for any physics project of any kind, right? You can choose to attack the technically difficult problems or not, and that's an issue of style. Different people have different ways of doing things. The core strategy for me throughout my career has been to develop new instruments Not to use existing instruments, but given a new scientific question, to develop new instruments to answer those questions. Oftentimes that's very challenging, but that's the cost of playing this game. Right?
And that's your style.
Yeah, that's what
Yeah,
I like.
you like the
I like
challenge.
to invent new instruments.
I see.
I like that very much.
I see. So what if, okay, so in this case, the student or a postdoc, he was able to do this?
Yeah.
In your career, was there any cases when you think, okay, a challenging problem you assigned to a student and they were not able to handle it?
Oh.
Are there cases like that?
Hundreds of times.
Hundreds of, okay.
Yeah. But usually the student is working on different aspects, different facets, so that even if one facet doesn't work, one of the other facets will work.
I see. So when that happens, what will you do? You change your student, put a different student on that, or?
Okay, that's a good question. Well, so if we talk about our colleagues, our student colleagues, from that point of view, I try to give the students with whom I have the privilege of working complete freedom to do whatever they want. So if a student is working on project A and they come to me and say, I'm not really interested in this anymore, I actually think this is already solved, or this is trivial or whatever, but I'd really like to work on Y, I just say yes. So if you give people their independence, they usually find their own way to success. That's been my experience.
I see. So that's also your style.
Yeah, just let them get on with it.
I see. So you have certain things in your mind that these are important questions, but if they are interested in different things.
Yes, and I think in our group we work on many different subjects. So usually a student has a wide variety of opportunities to pursue different projects. I don't manage it very carefully. Now, to come back to the technical question, suppose I have a bad idea. Of course, I've had many bad ideas. If it fails technically for an obvious reason, then I would try to take responsibility for that. The design failure, if it's mine, I would say, okay, well, this was a mistake, but I think the next generation of our design should do this. And so, I mean, the design drawing for our STMs is like 250 pages of drawings. And it's accumulated over now 25 years. And we're just beginning the 5th generation of our design. And I've made hundreds of mistakes in that process.
I see.
But from each mistake, you try and diagnose what was the problem, and the next generation of the design, you change the design and improve the performance. I mean, that's how cars are designed. That's how airplanes are designed.
Right.
Same deal.
Yeah, but I mean, nowadays STM also become a kind of popular tools. Most people, they just get from the commercial, right? Just spend some million of dollars and just whatever is available, I buy one. But you're different. You're trying to really pushing the limit of the technique.
Yeah. I'd like to find where is the next new opportunity in the field.
Can you tell us a little bit more about this 5th generation of the STM? What's the new advances comparing to your 4th generation?
So up to the 3rd generation, we didn't use room temperature UHV. We just used cryogenic UHV. Cryogenic UHV is 10 to the 12 times better than room temperature UHV. If the ambient low temperature is in the millikelvin regime, oftentimes an additional impurity atom will not arrive for a year, right? So you have no problems with that. But if you have to prepare samples at room temperature, then the first 3 generations, we couldn't do that. So the 4th generation, which we have now, they have room temperature UHV, and that produces, room temperature UHV means that you have to have the whole STM environment, which is 2 meters lower down inside the cryostat. It all has to be prepared at UHV at room temperature. And that's a tricky business. And in the design of that business in our 4th generation, I made a couple of mistakes. I have recovered from them now, but I didn't know anything about UHV, so they were naive mistakes. But 5th generation is to recover from them. and get now we use both Josephson and Andreev at millikelvin temperatures to study exotic superconductors. So we're pursuing that line.
So with this, you can cleave the sample at room temperature?
If you like,
that's the idea?
you can cleave at room temperature or you can cleave at low temperature.
I see. Okay, well, that's fantastic. Yeah.
It was hard.
I can imagine, yeah. Well, talking about, okay, that's the technique part.
Yeah.
Talking about the science directions.
Yeah.
You work on a variety of different directions.
Yeah.
And you mentioned this monopole thing.
Yeah.
And you mentioned that when you started, it was hard. Right? Some part is solved, some part is familiar to the community. It's hard to convince the community it's a problem.
Yeah, well, if you, especially if you make a new instrument whose output is unfamiliar, it's not in the textbooks, then you have a communication challenge. It's like making a telescope. Let's say you make a telescope in a new wavelength regime where it's never been made before, right? And then you take pictures of the sky. Well, they're going to look very different, right? And if there are skeptical colleagues, they'll say, well, that doesn't look like the sky to me. There must be something wrong with your telescope, right? So it's very hard to get over that barrier, right? And then after a while, people begin to realize, that probably is a valid picture of the sky in that wavelength. And then they begin to engage intellectually, and then finally it becomes understood. But there's a communication challenge involved.
So, well, in that case, the very initial, this proposal, right, this idea, then it's very important, right? So, at the time, how did you envision this problem?
I didn't, when I started out, I didn't know it existed. I have learned over the years that it does exist. But you more or less have to ignore it, because any kind of new physics instrument, which really moves the frontier, even by a small amount, is going to reveal new types of information that people are not familiar with. And the burden on the scientist is to be able to communicate sufficiently clearly that your colleagues and your audience can understand. Why is this different than the past? And how is it really working? And what's the consequence of these new capabilities? So that just goes with the job.
I see. So in case of this monopole thing, so what tricks or what did you do to really convince the community?
So for our first monopole experiment, we used
the squid one, right?
Squid one, yes. We used precedence. So there's a famous experiment by Blas Cabrera at Stanford, where he searched for fundamental monopoles by using a squid-based detector in the early 1980s.
Okay.
And for low-temperature physicists, that's one of the most beautiful and elegant experiments that you can imagine. And so when I became interested in the emergent monopole problem in pyrochlor lanthanides, where these are materials in which the quasiparticles have the quantum numbers of monopoles, I started to think about, was it possible to use the squid-based detector to detect the monopole fluid in these compounds? And then looking in the literature, it became clear that the most elegant experiment you would like to do, let's say you would just detect one monopole at a time, like detecting one photon at a time. That really wasn't possible because these are thermally activated plasmas. They're like intrinsic semiconductors. So at a finite temperature, there's a certain number of equivalent of holes and a certain number of equivalent holes and a certain number of equivalent of electrons. They're not holes and electrons, they're monopoles and antimonopoles. But in a millimeter-sized object, there are still trillions of those monopoles all moving around. So then we began to realize, and this was working with Steve Blundell at Oxford, that the main thing you should affect is noise. You have a monopole detector, but instead of one monopole at a time, you have 10 to the 18 monopoles, right? So then they started predicting using Monte Carlo what would be the noise spectrum of a monopole fluid. And as soon as that became clear, then the target for the experiment became very clear.
I see.
To detect the monopole noise, which we did.
I see.
So complicated story.
Yeah. Well, but that was a very nice word. We actually we try to follow with some similar designs. Yeah.
Yeah, well, those are tricky experiments when you mine down into the details. They're very difficult.
I see.
I mean, you're looking, so the Earth's field is around in the range of 10 to the minus 4 Tesla, but the monopole noise is in the range of 10 to the minus 12 Tesla. So you're looking for a random signal, which is 10 to the minus 12 of the ambient signal. And you know, the ambient magnetic noise signal in any lab is many orders of magnitude bigger than the monopole signal. So there's a lot of technology involved in doing those experiments.
I see. Yeah. So if one look at your publications, it's a long list of nature and science. It's all beautiful work. I imagine, you know, behind all these papers, of course, technique is very important.
Yeah.
But the idea is also very important, right? So how do you come up with all this nice idea that eventually leads to these beautiful works?
I don't know the answer to that question. I have loved physics since I was a kid. When I was in high school, the other kids around me would be looking out the window and watching football games. That was before mobile phones, so they weren't looking at their phones. But I would just be fascinated. There's a device called a tangent galvanometer, which is a device where you can send a pulse of current through some coils in the presence of magnetic fields, and it's on a torsional support member. So the currents then produce, a Lorentz force from the currents and the magnets produces an impulse to the object on its suspension. So if you send a bunch of current, then it starts oscillating. So 200 years ago, this was the most sensitive form of amplitude. Right. I just remember thinking, that can't be possible, because you're not actually changing the charge density in the wires. And there's no reason why a force on this object, I was just a young teacher, there's no reason why a force on this object should be due to the current. That doesn't make any sense, right? I was just fascinated thinking about it. And finally I learned about special relativity. It's because charge is conserved, and under Lorentz invariance there is a force. But it took me many years to learn that, right? So I like physics.
So it's the
I like the ideas.
Yeah. So right now, what's the biggest ideas or the dream experiment that you want to do?
For the monopoles,
Okay.
that's straightforward. We want to detect one monopole at a time.
In the solid state system?
Absolutely.
One monopole. Wow, okay.
Well, now we have a new device. It's a monopole current spectrometer. It doesn't measure noise, it measures current. It's like an ammeter, right? And our noise level now is about 100 monopoles per second. So we're very close. 2 orders of magnitude more improvement in the signal to noise, and we should be able to see individual monopoles going through. So that's a high priority.
I see.
We've just finished measuring the charge on the monopole for the first time. That was my previous high priority.
Wow.
But it's done.
Wow.
Yeah.
So that's still on the 227 system?
Yep.
Okay.
Dysprosium 227.
Okay. All right. What about the superconductor?
Finding a bulk topological superconductor, all helium-3 people have wanted to do that since the late 1970s.
You're close.
Yeah, well, that's you're close. To me, that's just that I'm really not convinced by the idea that topological superconductivity is going to revolutionize information technology. I don't really believe that. But at an intellectual level, having a bulk triplet topological superconductor opens so many scientific doors that at least I'm highly motivated to keep going in that direction. And if UTE2 is established in that category, it'll also provide guidance for us to find other materials with the same characteristic sets.
Yes.
So that what will happen, probably after I'm dead, but anyway, 20 or 30 or 50 years, there'll be lots of P-wave superconductors. It's like D-wave. Now we have plenty of D-waves.
Plenty of D-waves.
Yeah, we have no P-waves.
Yeah. Okay, well, fantastic. How do you like the Nobel Prize for this year?
It's interesting. My first response was negative when I read I'm aware of the beautiful work of these colleagues. I read the citation. I was a bit, probably just an emotional response rather than an intellectual response. And of course, you know, the number of Nobel Prizes per year has remained the same for 100 years, but the number of physicists in the world has grown by an enormous factor.
Yeah, for sure.
Right. So you know dozens of people who should get the Nobel Prize in physics, right? And so you're always thinking, well, how does person X compare with person Y, who's my friend, right? And, but anyway, I thought about it a little bit more later, and we discussed it last week when we were at Professor Louis Taillefer's 65th birthday conference. And I started to realize, you know, if you believe that physics is the fundamental empirical science for describing the world, and if use of that type of knowledge can open enormous new avenues for the human race to manage and understand and manipulate information, let's say through electronics, which functions like massive neural network systems, then indeed those colleagues did do work which is definitely of Nobel Prize quality. We just need to expand our picture a little bit of what constitutes physics. That's what I'm saying. If you expand to include our ability to manipulate very complicated networks and use them for technology and economy and so on, then absolutely, I think it's fun, fair, it's good.
Do you think this probably broadens the definition of physics?
I think so, a little bit. I would imagine that and I know a lot of people working on this problem, and I'm not, but it's a fascinating problem. If you have one of these multi-layer neural network systems, but where the nodes are quantum mechanical, right? Then what mental process, does that object execute? I think that's a fascinating problem.
Zara probably is working on it.
I have lots of people working on it, but I don't think anybody knows the answer. So one possibility is that decoherence would make such an object no different than our present, machine learning systems.
Well, then we need to low temperature.
Yeah, that's right. That's right. If you had a macroscopically coherent neural network, then what would its mental processes be? That's an amazing question. That's really interesting.
So, do you think if this all this AI and machine learning will revolutionize how we do physics?
I think that's a very deep question. So, I can remember when how we do physics didn't involve silicon-based code. When I went to Berkeley, joined Professor Richard Packard's group, and one of the first things I and the other new students in the group asked him was to buy a PC.
Okay.
But he wanted to know, what's a PC? So you see, as a tool, or another one is fast Fourier transform spectrometers.
Okay.
They were almost unknown at the beginning of the 1980s. Now they're so trivial you can have one on your telephone. Right? So in terms of powerful tools for detection, analysis, manipulation, and exploration of data, I'm sure that machine learning is already incredibly successful, and it will just grow in its utility. Okay, so at that level, I think it's absolutely wonderful, right? Now, at the level of imagination, of extraordinary new paradigms, which might be necessary to solve fundamental problems in physics, I don't know enough about machine learning to answer that question. But I'm a bit skeptical that the necessary level of pure imagination can be created in such systems, right? That's a deep philosophical question. I don't know the answer, but I'm skeptical. It's hard to imagine a machine learning system that would do what Einstein did in 1905. You just completely overturn what people have believed for 350 years and replace it with a completely new perception of the structure of our universe, in which the vacuum is a material, and that material has its own dynamics as detected by gravity waves. It's hard to believe that machine learning could do something like that. So I reserve judgment.
I see. Yeah. I kind of agree with that. But what about, for example, STM research?
Oh yeah, I'm sure it could make it efficient. I worked on a project with Professor.
Some type of paper.
Yeah, with Professor Una Kim. She was the PI, and we had a large archive of STM data, which had been examined by dozens of researchers over a period of more than 20 years. About 20 years. A very large archive. And they trained the machine learning system to just scan through the whole archive, searching for new phenomena. And they're training it to search for particular phenomena, right? So it wasn't unrestricted. But nevertheless, it succeeded in finding things that human beings didn't find in the data set. So at that level, I think it's tremendously powerful.
I see.
And we have a vast archive of spin noise from monopole fluids and other fluids, which is at present analyzed using traditional techniques, Fourier transform, power spectral density, etc. You could imagine that you feed the spin noise into a machine learning system, and it can diagnose other physics that human beings can't detect.
Oh, yeah.
Right? So there's great hope for the future and things like that.
So these are all data from your lab, right?
Yeah.
So if someone can combine data from all over the world, all the STM groups, you might even find more things?
That's possible. I mean, unlike astrophysics, there's no standard set for preservation or even encoding of data. So probably the data in our archive, which is now huge, is in a completely different format to the data in everybody else's archive. And without standardization of the structure of the data files and the meta information about how the experiment was done, you'd probably just get chaos if you shared the existing data.
Right.
But if we could achieve a standard, then machine learning could step in.
Wonderful. So probably the last question, you supervise so many postdoc students, and most are successful. I assume there are not as successful as others. So what do you think the important characters for a student or postdoc to be successful in this kind of field?
Curiosity, courage, and commitment.
Just like you.
Well, I lots and lots of people can be trained, and are trained very well by our universities, like this one, to understand what has happened in the history of physics, and to solve problems, and to pass their exams. And those are necessary skills. But that set of skills is not the set of skills you need to make a discovery, especially in an empty arena where there's very few existing, mileposts telling you what you should do. For that, you actually have to be an explorer. You have to be open-minded. You have to be curious to know the answer. Right? Then the other thing is, if you choose some really difficult problem, like, okay, what is dark matter, right? Now that's a serious problem.
Right.
I think to solve that problem, we probably need to open our minds a little bit more to other possibilities. And then if you sign up to attempt to solve a problem like that, then you need courage, because it might take decades. It might take your whole life. So, courage and commitment are also critically important. But the way we especially train people at the PhD level is more like an apprenticeship, right? We don't make them memorize books on how to discover something, right? We just throw them in at the deep end and say, now you have to learn how this profession works by doing it, and by emulating your peers, or sometimes fighting against your peers. And I think the apprenticeship style training that we provide now probably is the best way for both identifying and for helping people to reach the level of commitment and curiosity and so on necessary to make discoveries. I don't know of any other way. Right? The idea that you can have a training course to become a discovery scientist seems like a contradiction in terms to me.
But these are something that we didn't get until we get into PhD, right? Before that, it's more like a knowledge.
Yeah, well, I think in any advanced profession, right? Think of music, concert level musicians, or think of surgeons, or think of any advanced profession. In our present world, it takes a good 10, 15, 20 years of education before you can reach the level of understanding everything that's going on. And then and only then can you launch into the process of trying to improve the world, to change it. It's a very difficult challenge, both for the people going through that process and for the people who have to, for the people who have to help them. So, but as I said, I don't know any better way, so we better just keep going.
We pick it up this way.
We just keep going with our job. That's what I suggest. Right?
And so far, I mean, we enjoy it.
I love it. I couldn't do anything else. Along the x-axis, because that's important for you to E2. The B phase doesn't break time reversal, and it has no orbiting either. It's non-chiral. It's basically a vegetable. You could be fooled into thinking that it's an S-wave superfluid if you were not totally.